Okay, we're going to be starting a new chapter, Chapter 8, and the title of that chapter is Right Triangles and Trigonometry. We're going to do the first three sections regarding right triangles. Some of that's going to look familiar to you. We're going to do that now, and then we're going to do the trigonometry sections a little bit later in the school year. The first section here is titled Geometric Mean, and we can also call it Similar Right Triangles. We have been looking at similarity between polygons and triangles, and here we're going to be looking at what that looks like specifically in right triangles. So far we've been looking at proportional relationships between similar triangles. We've shown that the angle bisectors, the altitudes, and the medians scale to the same proportionality. We're going to look at what that means inside of a right triangle, and we're going to learn about two new concepts here. The geometric mean between two numbers, and we're also going to look at what happens when we draw an altitude inside of a right triangle between the right angle to its opposite side, which is the hypotenuse, and what's created from that. Okay, let's take a look at new vocabulary. Geometric mean. So when you hear the word mean, you should be thinking average. That would be summing a set of numbers and then dividing that sum by the number of numbers that were in the sum. Geometric mean is a little bit different. And in this chapter, we're mostly going to be looking at the geometric mean between two numbers. So the geometric mean between two numbers, I'm going to say, is equal to the square root of their product. And that's all we're really going to look at in this chapter. But you should know that here, of course, we get lazy and we don't put the 2 for the square root. But there is a 2 there. But if we wanted to look at the geometric mean between three numbers, it would be the cube root between those three numbers. Or between four numbers, it would be the fourth root, etc. We're not going to take a look at any of this in this chapter, but you should know that it exists. Everything we look at here is going to be the square root of the product of two numbers. So let's take a look at what I mean by that. We've looked in the past, when we started similarity, looking at ratios. So let's say A is to C as D is to B. And of course, C cannot equal to 0 and B cannot equal to 0. And we can rewrite these proportions as A is to C using the colon as D is to B. And we've talked about this in the past, that these two numbers here in the middle are called the means. And these two here on the outside are called the extremes. So this concept of geometric mean occurs when the means, here in my example C and D, are equal. So if you look up here in our definition, I've replaced C and D with X here to show that they are equal. And when that happens, you've created a geometric mean between A and B here. So if we rewrite that over here, A is to X as X is to B, or A is to X as X is to B, then we can cross multiply and we get X squared equals AB. Take the square root of both sides, and we have X equals the square root of AB. So the geometric mean is the square root of the product of two numbers. And here they show an example. Find the geometric mean between 9 and 4. Well, if we take their product, we get 36, and the square root of 36 is 6. So therefore 6 is the geometric mean between those two numbers. So let's take a look at another example. Find the geometric mean between 2 and 50. We would say the geometric mean 2 is to X as X is to 50, and in this case X is our geometric mean, and we're going to cross multiply. And we get x squared equals 100. And therefore, taking the square root of both sides, you should see that x equals 10. Another example, find the geometric mean between 3 and 12. We would have 3 is to x as x is to 12. And x squared equals 36. And hopefully you can see that the square root of 36 is 6b. All right, let's take a look at what the bulk of this section is on. Here we have a right triangle, ABC, and we're going to draw an altitude originating at that vertex C where the 90 degrees is. And of course, an altitude drops to the opposite side perpendicularly. So we have this segment now being created, CD, coming down. And what happens is very interesting. And I'm going to try to split out all three of these triangles now. So here we've got a medium triangle that's created, ACD, and we have a little baby triangle here, CDB, and then we have the original. And we can show very easily by just rotating and flipping a little bit that all three of these triangles that are created are similar. So I'm going to draw them. I'm going to draw the largest first. I'm going to put the right angle down here on the left, so this would be B and this would be A. And now I'm going to flip and rotate that medium triangle, trying to show corresponding angles here. So this would be D, this would be A, and this would be C. And finally, the little baby triangle, the right is at D, B, and C. Now, why are these all similar? Well, angle A here in the big triangle is also in the medium triangle, and by the reflexive property, it's congruent to itself. Likewise, angle B is in the large triangle here, and it's also in the baby triangle, and it's congruent to itself by reflexive property. So hopefully by now you're starting to see that we've got two pairs here, a single arc and the right angle, a single arc and the right angle here. So by third angle theorem, this angle here has got to be congruent. And likewise over here we've got the right angle and the double. So by third angle theorem, this angle has to be congruent. So we can write a statement of similarity here. I'm going to start with the large triangle. A, B, C is similar to triangle A, CD, we would have to put that in that order, is similar to triangle C and BD. In every case, the right angle is in the third position. In every case, the single arc angle is in the first position, and the double arc is in the second position. And that was just determined by how I wrote these first, and these are now in corresponding order. So you can imagine that this set of three right triangles, three right similar triangles, sets up quite a lot of proportions. And because some of these segments are in multiple triangles, you can start to imagine that their value or their length becomes a geometric mean in a proportion problem. Before I leave this chart, I just want to give you some advice on solving these types of proportions, and it's very helpful to split out this type of drawing into three triangles, labeling the triangles for what side lengths you know and have, and then labeling what side lengths are your unknowns and that you're trying to solve. And I personally find it very helpful to put them in corresponding orientation, let's say. So here I've got the long sides all vertically up here on the left. I've got the hypotenuses all to the right, and the short sides over here horizontally on the bottom. And I think you're going to find this helpful quite a bit in solving these types of problems. So let's take a look at this triangle, write a similarity statement. Again, I find it very helpful to split out the triangles. There's the largest one, here's the medium, and here's the small. I don't know why, but I always seem to want to put that the right angle down in the lower left, and in which case on the large triangle that would be F. G is at the top of the long side, and E is over on the other side of the short. Looking at the medium triangle then, I'm going to have to rotate and flip the right angle here. If you can see on the medium in the red is H. The top of the long side is G, and the other side of the short side is F. And then finally, looking at the baby triangle, the right angle is here at H, and the other side of the long side is F, and on the other side of the short side would be E. So let's write a statement of similarity. I'm going to start with the large triangle, GFE. In this case, I put the right angle in the middle, is similar to GHF. That's the medium triangle, is similar to FHE. And this here would be our statement of similarity. From that, obviously, we can write a long proportion of all of these proportional sides, and we immediately know what angles are congruent. Okay, let's see if we can write a similarity statement for the three similar triangles in the figure. Again, we start with a right triangle, drawing an altitude between the right angle and its hypotenuse. And let's just take a look at the large triangle here. Almost in every case, we have LMN, LMN. So M is the right angle. Let's just write that here. LM is the right angle. Keep an eye on that. Now let's look at the medium triangle. In the medium triangle, we have LMO. We can see right away that the O is the right angle. So let's see where that falls. O, 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 and O. So right away, we can eliminate one of these possibilities, and that would be D. I hope that you can see that. Here, the right angle, M, is in the middle position. Here, the right angle is out of sequence or out of correspondence. So I would eliminate that as a choice right away. Now let's go to the small triangle. We have MON. O is the right angle. So let's just mark that O, O, and O. Okay, so we can see for the right angles here, they're all in corresponding, well, actually no, I'm sorry. We can eliminate B here as a possibility as well, because right here, this O is in the wrong position. So we're down to A and C. Now we're going to have to start to look at the long sides and the short sides. In A, we see that the top of the long side, LM, is vertex L. All right, so I'm going to change color here. The top of the long side is L. So let's go to the medium triangle. The top of the medium triangle, here's the medium triangle. The top of the long side is also L. Unfortunately, that did not line up. So we can eliminate that as a possibility right there. So let's take a look at our final answer. C. We've got L at the top of the long side, L at the top of the long side of the medium triangle, and M here in the baby triangle is the top vertex of the long side. So that's in the perfect position. We've already looked at the middle vertex here being the right angle. N in the large triangle here, N is on the other side of the short side here, and in the medium triangle, M is on the other side of the short. And finally, in the baby, N here is on the other side. This is on the other side of the short side. So everything completely lines up perfectly in option C. Okay, here are two important theorems, and they arise when we write our proportions. The first one is the geometric mean altitude theorem. So here we've labeled this altitude h for height. We have a right triangle ABC, and we've dropped that altitude down to the hypotenuse AB, creating these two segments here labeled x and y. So hopefully you can see that this small triangle here and the medium triangle here share this altitude as one of their legs, and that in fact means it's going to become a geometric mean. So let's sketch those two triangles here. I'm going to just move, oops, I'm going to just sketch ADC as is. I'm just kind of keeping its orientation identical. And that's the small triangle. And then I'm going to rotate CDB. It's a little bit bigger. I'm going to rotate that around. C would be here, and D is the right angle here, and I'm rotating this around in that direction. So B becomes here. And the only reason why I'm doing that is just to show correspondence here. It just makes it a little bit easier. So CD is labeled H, and CD is labeled H here. AD is X, and BD is Y. So now that we have this corresponding diagram, and I'm sorry that it's drawn over this triangle, maybe that's a little bit confusing, but let's take a look at how we can see that X here, AD, is to H, as, now let's look at its corresponding side over here, H is to Y. And if we cross multiply, we get H squared equals XY, and take the square root of both sides, so H is the square root of XY. Now what did we just see here? H, that altitude, basically the length of that altitude, is going to be the square root of these two segments that are created from that altitude. Therefore, H is the geometric mean. H is the geometric mean, that altitude is the geometric mean between these two segments. Okay, now let's look at the next theorem, the geometric leg theorem, geometric mean leg theorem. And the theorem states that there are two additional geometric means that are created from the legs, from the non-hypotenuse here of the original triangle. So here, looking at the leg B, B will be the geometric mean between the entire hypotenuse and this little segment here that's adjacent to B. A, the other leg, will be the geometric mean between the entire hypotenuse and its adjacent segment, Y. Let's take a look at why this is true. So here I've got a sketch of our original ABC right triangle along with its altitude drawn, and I'm going to prove one of these geometric means and the other is really identical. So let's take a look at why B is the geometric mean between the hypotenuse of the original triangle and this segment here, X, that is adjacent to it. So let's start out by drawing the large triangle, and I'm going to rotate it a little bit. I'm going to put C down here, B and A, and I'm going to look at this small triangle here that's next to it, and I'm going to look at it in corresponding orientation here. So D is the right angle, and we've got A here and C here. So let's label our sides that we know. AC is B, and AC is B. And the entire AB hypotenuse is labeled as length C. And the side AD over here is labeled X. So we can see that BA hypotenuse is to CA hypotenuse, as CA over here on the big triangle is to DA over here on the small triangle. And you can substitute C is to B as B is to X. And if we cross multiply, we have B squared equals CX. And therefore, taking the square root of both sides, we have B equals the square root of CX. Therefore, the conclusion is B is the geometric mean. So this leg here of the original right triangle is the geometric mean between the hypotenuse and this segment that is adjacent to it. And you can go through the exact same concept here using this medium-sized triangle and the original triangle to prove that A is the geometric mean between the entire hypotenuse and this segment here that's adjacent to it. Now, how can we use this information? Here in example 3, we're asked to solve for C, D, and E. So C and D are legs of the original right triangle, KLJ, and E is the altitude. So I strongly recommend not memorizing necessarily the theorems, but getting used to seeing the 3 similar triangles. So this is the original here, KLJ. I've got the right angle down in the left. Therefore, KJ is side D here, KL is C, and LJ is the length of the entire hypotenuse, which is going to be 24 plus 6, or 30. So that's our big triangle. Now let's draw the medium-sized triangle. And in the medium-sized triangle, the right angle here is M, and the top of the long side is L, and over here will be K. Let's label whatever sides we know. LK here is the hypotenuse of the medium triangle, so opposite this right, so it's the hypotenuse. So we're going to label that C. LM is 24, and KM is labeled E. And finally, let's draw the small, oh boy, I didn't do a good job of drawing that very small. Let's try to draw this a little bit. And that right angle on the small is M, the top of the long side is K, and over here on the other side of the short is J. So we know JM is labeled as 6 units, and KM is labeled E, and KJ, the baby triangle's hypotenuse here, opposite that right, is labeled D. So hopefully you can see a whole bunch of proportions that we can write and solve. So which one do we go for first? Well, I would look around. We know here the hypotenuse, and we have a label C here for the hypotenuse of the medium triangle, and C for LK, the long side, and we have a number for the long side. So that's a proportion that we can write right away and solve for C. So let's go ahead and say LJ hypotenuse is to LK hypotenuse, as LK long side is to LM long side. Substitute in. So LJ is 30, and LK is C. LK in the medium is, the hypotenuse over here in the medium is also C, and LM is 24. So we can cross multiply, and we can get C squared equals 720, and therefore C equals the square root of 720. And let's try to simplify that a little bit. C equals, the first thing that comes to my mind here with 720 would be 72 times 10. And we can write 72 as 36 times 2. 36 is a perfect square. And 10 is 2 times 5. So you can see we have two perfect squares here, the 36 and the 4. So we can take those out. So C equals, the square root of 36 is 6, times the square root of 4 is 2, and we have the square root of 5 still left. So C equals 12 square roots of 5. Okay, let's look at where we have more information. Taking a look at the large triangle again here, LKJ, we have the hypotenuse and we have a side labeled D, which is the short side. Over here in the baby triangle, we have an hypotenuse, D, and a short side in which we're given a number, 6. So that's a good proportion that we can set up here. And we could say the hypotenuse 30 is to the hypotenuse D in the baby triangle, as the short side D in the large triangle is to 6 short side in the baby triangle. And if we cross multiply, we have D squared equals 180, and solve for D, and D equals the square root of 180. And we can try to simplify that. This equals 9 times 20. And we've got another perfect square in there, 9 times 4 times 5. So therefore, the square root of 180 is the square root of 9, which is 3, square root of 4, which is 2. So we've got 6 square roots of 5. Finally, we can look to solve for E, the altitude here. Looking at the medium triangle and the small triangle, we have the short side E and the long side E here, and we have the long side 24 and the short side here 6. So we can set up that proportion, 24 long side is to E long side, as E short side is to 6 short side. And we can cross multiply here, and we get E squared equals 144. And therefore, if we take the square root of both sides, 144 being a perfect square, E equals 12. Sorry for the messy chart, but hopefully you get the idea of how these theorems work. And rather than memorizing the theorems, you can always line up correspondence here by splitting out all 3 triangles and solving for each of the unknowns. All right, let me try an example where we use the theorems rather than splitting out all the triangles. I'd like you to get used to both. So let's take a look here for what's being asked. We're being asked for one of the legs of the original right triangle. So we're looking at the geometric mean leg theorem, and that states that this side here will be the geometric mean, so E will be the geometric mean between the entire hypotenuse length and this segment here that's adjacent to it. So what does that look like? We can say that, setting up a proportion, E is going to be our geometric mean, and it's the geometric mean again between this entire hypotenuse here, which is 20, and the side adjacent to it, which is 16. So cross multiply and solve. E squared equals 320, and take the square root of both sides, and E equals the square root of 320. And the example asked us to find that to the nearest tenth, so I'll let you do that. Taking a look at a real-world example, in this case a kite. Ms. Alspach is constructing a kite for her son. She has to arrange two supporting rods so that they are perpendicular. By the way, that's a definition of a kite. The shorter rod is 27 inches long. If she has to place the short rod 7 1/4 inches from one end of the long rod in order to form two right triangles with the kite fabric, what is the length of the long rod? So what's being asked for here is this long rod. What is the length here? All right, let's see if we can make our sketch a little bit bigger. So hopefully you can see we really only need to look at the top here, since it's completely symmetrical and we're looking at this right triangle up here. We have a right angle coming down with an altitude, creating three similar right triangles. If the short rod here is 27 inches long, then we know that half of that is 13 1/2, and that's actually going to be the altitude of our triangle. And we're told that this piece here is 7 1/4, so I'm going to label that 7 1/4. And we're being asked for this entire hypotenuse length, the long rod. So let's label this piece over here x, and then when we solve for x, we can just add it to 7 1/4 and get our length. So if we want to use the geometric mean of the altitude here, we know that the altitude is the geometric mean. This altitude here is the geometric mean between these two segments that are created in the hypotenuse. So let us say, we're going to write that out. The geometric mean, I'm going to shorten that for GM, equals the square root of the product of two numbers. We know that the geometric mean is 13 1/2. And that's the square root of 7 1/4 times the other segment, or x. Now how can we solve this? So our unknown here, x, is underneath the radical, and I need to free that up. And the inverse operation of a square root is a square. So I'm going to square this side, and if I do that on one side of that equal sign, I've got to do it on the other. So the square of 13 1/2 is 182 1/4. And the square of the square root of 7 1/4x would be just 7 1/4x, because these are inverse operations of each other, so they undo each other. And if I divide 182 1/4 by 7 1/4, I get x. Oops, I get x roughly equaling 25, a little bit over 25 inches. So the entire length here of the long rod then would be 25 1/10 inches. And another real-world example, airplanes. A jetliner has a wingspan BD of 211 feet. The segment drawn from the front of the plane to the tail, which is labeled AC here, front to back, intersects BD at point E. If AE is 163 feet, what is the length of the aircraft, meaning AC here, to the nearest foot? So again, we're being asked for that hypotenuse, really, of the original right triangle. I'm going to draw it over here. We have B, A, C, and the altitude coming down to E. Now, if wing to wing is 211 feet, then our altitude is going to be half that. So we can divide 211 by 2, and we would get 105.5. And AE is 163 feet. And if we can call EC X, that will help us determine what this entire length AC is. Again, very similar here. BE is the altitude, and that is the geometric mean. So we have 105.5 equals the square root of these two segments here, the product of them, 163 times x. If we square both sides, inverse operation of the square root, we get here, actually I'm going to show that. We're going to square both sides here to get rid of that radical. Then I have 11,130 and a quarter equals 163x. If I divide both sides by 163, I get roughly 68.3 feet. So x here is 68.3 feet, and I would need to add that to 163 to get the full length nose to tail or segment AC, and that is roughly 231.3 feet long. This is typically a challenging section for many people. It does require a lot of visualization skills. You can memorize the theorems, although our memories are faulty, so it's easy to forget them very quickly if you're not using them. So I always recommend that initially when getting going in this section, that you take the time and draw the three triangles, put them all in the same orientation so that you can easily see the proportions setting themselves up. Okay, thanks. Hope this helps. Take care.